let's finish off by talking about finding the Taylor series of a function. So remember, a Maclaurin series was a way of finding a power series centered at 0 for a given function. Well, sometimes we might not want to center at 0. For example, if the function isn't defined at 0, we might not want to center there. Right? There's other reasons as well. We could want to center somewhere else. So, recall that a power series centered at somewhere other than 0 takes the form like this. So what we're doing when we're trying to find what we're going to call a Taylor series is we're trying to find a power series like this associated to a function. In other words, we're trying to find this. We're trying to find the coefficients so that this is true. Right? Well, what probably isn't a big surprise here is that the procedure to do this is going to be exactly the same as we did for finding the Maclaurin series, except instead of plugging in x equals 0, we always plug in x equals a because of all these x minus a's here, right? So you'll find that c0 is f of a. You'll find that c1 is f prime of a. You'll find c2 is going to be f double prime of a over 2, and so on. Right? You're going to find that exact same pattern as you go through. So generally speaking, the kth coefficient of a Taylor series is going to be the kth derivative at a over k factorial here. All right? In other words, so let's define here a Taylor series. All right? So we would say that, suppose f has derivatives of all orders on an interval, right, of the form a minus r to a plus r, right? In other words, the center of this interval is a, and we move out a distance of r in either direction, right? So this series should be valid on that whole interval. Okay? Then we say that the Taylor series of f centered at x equals a, this is given by f of a plus f prime of a x times x minus a, okay, plus f double prime of a over 2 factorial x minus a squared plus ... which is just equal to the sum from k equals 0 to infinity f kth derivative at a over k factorial x minus a to the k. Right? This right here is the Taylor series for a function centered somewhere other than 0. Right? So the process doesn't actually change that much. In fact, it's basically exactly the same. We just, plug in a instead of 0. Right? And one nice thing here is when we plug in x equals a, all of these terms go away except for just f of a. Right? So that's sort of what it means to be centered there. Right? So the interval is centered at a. All of this sort of starts at f of a here and then kind of grows away from that. Right? So this is sort of the idea behind centering a function somewhere. So let's look at an example of that. Right? So a good example, remember I said that, you might want to center a function somewhere else depending on where it's defined at. Well, let's say we had the function f of x equals 1 over x, right? This function here isn't defined at x equals 0, so there's no way we can get a Maclaurin series for it at all. On the other hand, we can find a Taylor series at literally any other point. So let's find a Taylor series at centered at a equals -1, let's say. Right? So just like with Maclaurin series, we're going to make a big chart and try and find a pattern in the derivatives. Right? So here we're going to make a chart with k, fk of x, and ultimately what we really want is the kth derivative at -1. This is the column we want to find a pattern for. Right, so 0, 1, 2, 3, 4. Hopefully that's enough, but we can always do more if need be. Right? So remember, the 0th derivative is the function itself. Let me space these out a little more. Right? The first derivative is going to be -1 over x squared. The second derivative is going to be 2 over x cubed. The third derivative is going to be -6 over x to the 4th. Okay. So here, when we plug in -1, we're going to get 1 over -1. Going to have -1 over -1 squared, which is, so this is -1, this is -1. This thing here, this is going to be 2 over -1 cubed. So that's -2. Here, we're going to have -6 over -1 to the 4th. That's -6. All right. And if we do the next one, in case you can't see the pattern yet, right, the next derivative, this is going to be 24 over x to the 5th. So here we'll have 24 over -1 to the 5th, which is -24. Right? Now again, I simplified at each step here just to not make a mess. But you could also say up top here, it would help to say, all right, that's 2 times 3. This is 2 times 3 times 4. Right? So here, what you'll find is this is -0 factorial. This is -1 factorial. This is -2 factorial. -3 factorial. -4 factorial. And in case you're wondering, yes, there is parentheses around this. Remember, if you want to have like a 2-digit thing or a 2-part thing applied to, with the factorial applied to it, you need parentheses around that. And we don't have factorials of negative numbers. At least we don't, as we've defined things. So the pattern we see here, right, hopefully you can see it, is that the kth derivative at -1 is going to be negative of k factorial. Right? Hopefully you can see that. And so the Taylor coefficient here is going to be, so we get -k factorial over k factorial. But as we learned, these this one's simple. We didn't even need to learn anything. This just cancels out to -1. And so we get that, well, f of x, which is 1 over x, this is equal to the sum from k equals 0 to infinity of -x to the k. All right? Oh, sorry. I did that wrong. X minus -1 to the k. Right? So this is x equals 0 to infinity of negative x plus 1 to the k. Now the question is, what is the radius of convergence here? What is the what is the interval of convergence? Well, we can find the radius actually. Again, we should, to verify it, we should use the ratio test, but this thing, the only place it's not defined is at x equals 0. Negative 1 is 1 unit away from x equals 0, so the radius of convergence is actually going to be 1. I'll let you test that on your own, right? But finding a Taylor series really isn't that bad. Right? It's the same process as finding a Maclaurin series, just instead of plugging in 0, we plug in whatever number we need to.